Yeah, so as I started to say, thanks, Matt, for squeezing me in. We had a little technical difficulty a couple weeks ago. So I today will speak a little bit about NanoHub and how we've viewed tools and how they should be used in the evolution over time, and how BOINC fits into the picture today. So for those of you who've attended this meeting before, some of this may be a little bit of a rehash, but for people new to the group, I thought I would start by describing a little bit about what is NanoHub. So NanoHub is a science gateway in today's vernacular. It's a place where people come to collaborate. They do multitude of simulations. Hopefully they can explore data. And they are stimulated in some way to learn some new things about nanotechnology. NanoHub is built on the Hub Zero platform, so there are other science gateways that are using the same infrastructure that could also benefit from tools like BOINC. By way of numbers, in the past year, we had approaching 2 million users, which users roughly equates to viewers on a website. About 220,000 of those 2 million bothered to register and tell us who they were and what they like to do, which helps drive the site. Relevant to today and what we do with BOINC is that roughly, again, about 10% of those people actually run simulations on NanoHub, so about 23,000. Tools on NanoHub are community submitted, registered, created, maintained, and there's 675 or so of those, covering a wide range of complexity or simplicity. Some are used strictly in classrooms, some are more research-based. And basically, the image here is just to show the sort of the width and breadth of coverage of various tools on NanoHub as it relates to nanotechnology. So one of the fundamental backbones of the platform or the Science Gateway is the ability to do a collaborative computation. So the tools are, as I mentioned, they're supported and built by the community that runs them and uses them, and they're made available to anybody, typically anybody who wants to use them. So from a user point of view, you can come to NanoHub. You don't have to download code. You don't have to build code. You can just run the tools. And this is the same point that David was making last week, and is trying to provide a simplified, streamlined, easy way to fire up BOINC. It's a very similar strategy to what we do with NanoHub tools. Developers are provided with a fairly rich Unix platform to build on, or Linux platform, with source code management and various other GUI development tools. So we have, if we have 20,000 people running simulations, how do we support that? And this is a sort of the high level view of how we do that. So at the center of everything, there's a website and a web server. We have 15 to 20 what we call execution hosts, which are just typically not the newest machines on the planet, but there are a bunch of machines in a rack that can host simulation computation. And in addition to our own sort of hosted environment, we make or provide access to external resources such as Exceed or Open Science Grid or BOINC. We've also done some work with cloud providers or platforms. So now maybe a little bit more to the sort of the evolution part of the talk. Going back to the beginning in roughly the early 2000s, everything was basically the only way you would do a simulation was what I refer to here as on demand. You would decide to run a tool, you would initiate the tool, there would be some sort of user interface, you would enter the values that you want to run, and you would push run or simulate or some such button. You'd wait a few minutes if it's a small simulation, and results would come back and they'd be presented. So the major feature here is that it's intended to be an interactive environment, and that if when possible, that results should be delivered quickly. So it's not the batch sort of HPC environment. So the way we do this, I mentioned the idea is to be fast as we can. We added a caching system with the idea that, why run the same simulation 50 times to generate the same answer. So probably 10 years ago, we added a sort of this caching system where when the user requests a simulation to be run, we first check the cache, and if the result is already available, it's delivered immediately. Otherwise, it's executed on either locally or remotely on HPC. This basically enhances the user experience. The next sort of development in the evolution was the addition of the ability to provide what we call uncertainty quantification simulation, so that you could get not just put point values into your simulation, you could provide inputs as distributions. And when you did this, your outputs also are returned as distributions. And this is accomplished by some well-established statistical methods for selecting various points in the range of space that you want to simulate. The tool developers don't have to do any additional work to take advantage of this opportunity. It's built into the UI system. It was thought that this would be widely used. It turns out it is not used a whole lot. The other point here was that there's the potential here to greatly increase the number of the simulation load, basically the requirement for a simulation. And then the latest thing, which is what we're working more on mostly today, is what's called here exploratory simulation, whereas we can use the cache results, and rather than users requesting individual simulations, they can run a tool that can sort of, in some sense, browse visually the results that have all been previously generated. So to do this, it takes a large number of simulations to cover the dimensions of the simulation space. And to do this, we're using BOINC to a large degree. Let's see. So pretty well already covered this, but another couple of points here is to do this, we have to enhance our visualization techniques, and I'll show you an example of that. One of the benefits here is you can generate surrogate models from this approach and use the models which are computationally less expensive in further analysis. And another activity that has been greatly enhanced in the last year is offering of online education services, which is another, perhaps a vehicle where this mode of simulation would be useful. So with all of this, as I mentioned, large numbers of simulations were required, and the challenge, the last time we had a meeting, which is 18 months or 2 years ago now, roughly, the challenge was to do 10 million simulations in a year using BOINC, or roughly almost 1 million a month. So structurally, the way we do this, this picture looks very much like the previous one. there are two additional blocks added here. One is labeled SpecBot, which feeds the cache queue, and BOINC, which has been added to actually do the simulations. So a good portion, most of the Rapture tools are built on something called Rapture, which has a structured input in XML format, which allows us to do this. And I mentioned earlier, there's like 675 tools. Well, there's about 150 or so that we actually use BOINC to support and generate these large scale results. The SpecBot program can take an existing result and basically do perturbations around that solution to generate new simulation requests. Take those perturbations and feed them into the queue. And then BOINC will examine the queue, and when there are enough jobs in the queue to make a batch, make up a batch of a single tool, submit those to BOINC and await the results, which are then stashed into the archive. So let's see. Yeah, so basically went through this one already. And I mentioned the challenge was to do 10 million jobs in a year, and we're just approaching that. For a couple of months worth, we reached that level towards the end of 2019. And then we were, Hub 0 moved from Purdue to SDSC, which interrupted everything. And it's taken me a while to get back on track. But in the last couple of months, I've started things up again. And so we're hopefully going to reach this level again. So I thought maybe rather than just talking about it, I could give a short example of the sort of different modes of the way these tools work. So the first one, and I'll take a chance here. So did the screen change for everybody?
Yes.
Yes. Okay, perfect. So I thought I would take a chance and actually run the tool live, so to speak. So this is the traditional approach where it's just you have a UI, there's some fields that you fill in. You've entered all the values that you want, and basically you hit simulate. So in this case, it's just the default values for the tool. So the results were already, basically pre-computed and in the cache, and then they're immediately provided. The uncertainty quantification is signified by these symbols. So you can, rather than us putting in a specific point value, you can specify either uniform or Gaussian distributions. After you would fill that in, again, you would just push simulate, and the results that would be required would be generated and executed. The newer approach, in the sort of the exploratory approach, I have the wrong tool. Let me, well, okay. All right. In the interest of time, I'll skip. I had a second example, so we'll try that. So in this case, instead of doing individual simulations, there's a tool has been created to view the existing simulations, so that have previously been cached. They've been sort of indexed and put into a database to make it even faster. So this particular tool is for a DFT simulation. So there's a choice of material, there's a function choice, and what kind of output do you want to examine. So there's several choices for each of these. And what immediately appears is, as a function of a couple of the inputs, which are the number of K points and a cutoff value, you can see the spread of results as they've already existed, which is shown here in the diagram. There's a couple of different offerings for the way to view the results. So this is a sort of a two-dimensional plot. There's also a sort of a 3D space, and you can sort of flip this around and change your camera point of view and examine that. There's this correlation function, which is potentially quite useful. So you can report the correlation between the different input fields and the output results. So if there's a high degree of correlation, that's useful. If there's a extremely low degree of correlation, that also is very useful. There's also features from here to, again, put in some input values, generate some new simulations in the more traditional sort of sense. But after they're done, what happens is they're added to these diagrams. And so you can fill in the space if there's something missing. And that's also been very useful and productive. So that sort of a quick tour. And this is the one that I couldn't show you, but it's again, this is the existing results. There are several curves on each plot. If you wanted to, if there was a curve missing here, you could pick that point, generate values for it, and update the diagram. And then the results, as soon as you create them, are available to everybody. So everybody will see the updates. So I think 15 minutes went by pretty quick. But if there's any questions, I will attempt to answer them. Thank you.